Hello everyone, and welcome to our DFIR webcast, How Memory Forensics Will Help You Lose Weight and Look 10 Years Younger. I'm Jason Keeler with the SANS Institute, and I'll be moderating this webcast. Today's featured speaker is Jesse Kornblum, Network Security Engineer for Facebook. Before I turn things over to Jesse, the Q&A portion will take place during the webcast. Please feel free to submit your questions at any point by using the chat window. Right now, I'd like to introduce our featured speaker, Jesse Kornblum.
Good afternoon, everyone. Thank you very much for attending this webcast. As mentioned, today we're going to be talking about memory forensics and how it will help you to lose weight and look 10 years younger. First thing I want to say up front is that all the things I'm going to be demonstrating this afternoon are covered in the course that I teach, Windows 4 526, Windows Memory Forensics in Depth. Today we're just going to do a demonstration, not going to talk about the actual techniques or programs that you use to recover this information. That being said, this is a very interactive talk. You're welcome to ask me questions at any time. Go ahead and please type them into the chat room. I will do my best to respond to them, but in this format it may not be possible for me to respond immediately. Now, this being, of course, an interactive session, though, you get to ask me questions. It's only fair that I get to ask you questions. But I will give you a hint. The answer to every question is, it depends. So with that, let's go ahead and get started. So first things first, I wanted to say, this is a real talk, that memory forensics will help you lose weight and look 10 years younger. And the proof for that is in the pudding. This is a picture taken of me. I'm the one there on the left. This is a picture of me taken in 2004. And it's right before I started working on memory forensics. And is, well, I'm not exactly proud of it, but that's what I looked like back then. And this is me now. As you can see, I've changed a little bit. My tastes in farm animals have changed. I've moved from goats to horses. Oh, also in this picture, I'm the one on the left again. My tastes have changed a little bit, and also I have lost weight and kept it off, thanks to the power of memory forensics. Now, of course, okay, slide 5, I don't see there. Of course, memory forensics is part of this complete investigative plan your agency puts together for you. And these results are not typical. Not everyone loses weight just from memory forensics. There might be some other things, balanced diet and exercise and so involved. Please consult with a doctor before beginning any sort of memory analysis program. Now that being said, let's get down to business. Let's talk about memory forensics. And so tonight we're going to be talking about the different kinds of things that you can get from memory forensics. And I'm actually just going to be highlighting 5 of them tonight. Encryption keys, command lines, process ID relationships, automated high-low analysis, and finally, hibernation files. They look back in the past to all of these other things to a one-shot view of the past from the machine that you're examining. So let's go ahead and jump in. Let's jump in at the start with encryption keys. And to do that, I'm going to tell you the story of why memory forensics is valuable. This gentleman was Rajiv K. Mitra. And Mr. Mitra lived in the city of Madison, Wisconsin, and he liked to amuse himself by broadcasting the audio from porn movies onto the police radio frequencies. In other words, on the radios that the cops had in their cars, they would suddenly hear porn. Needless to say, Madison's finest were not exactly happy about that, and so they set about finding Mr. Mitra. And through some triangulation, they finally caught him, and he was arrested. And he was brought up on charges for those illegal broadcasts. But in the process of going through his computer, yes, they found all sorts of plans for being able to broadcast on the radio frequencies, but they also found encrypted files which they believed contained child pornography. The file names were indicative of child pornography. But unfortunately, the files were all encrypted. Although they could get the file names, they couldn't get the file contents. Mr. Mitra was charged, unfortunately, then with just the broadcast charges. No charges filed related to the child pornography. And Mr. Mitra was convicted, and he went to federal prison. While Mr. Mitra was in federal prison, the science of memory forensics was developed. And the case agents stayed with the case and decided to go back and look at this original evidence again, this time using memory forensics. And they found actually a Hibernation file in there. And the Hibernation file contained the encryption key, which allowed them to decrypt the files, and sure enough, they contained child pornography. About a few months before Mitra was scheduled to be released from prison, he was indicted and then convicted on multiple counts of possession and creation of child pornography. And Mr. Mitra actually ended his life in prison. He never made it out. It is the power of memory forensics in that it can take a case which was previously unsolvable, which previously no action could be taken, and brings it to a conviction. Now, how did all that work? Well, what you can see here on slide 8 is, actually, you can't see anything on slide 8, nor slide 9, 10. Hang on. Okay, I don't see anything from slide 8. Jason, is something going on there that I should know about for the missing slides here? It looks like we're missing 8, 9, and 10. Okay, we're going to take a pause here. We're going to resolve these technical issues. Okay, I can see part of slide 8 there, but it looks like it's, there we go. Okay, now I can see the whole slides. Could I get from the audience a thumbs up or a clap if you can actually see the slide here? Okay, all kinds of happy reactions. Wonderful. Thank you very much. Okay. All right. So let's back up. Let's talk about encryption keys and how they work. The neat thing about encryption keys from the purpose of memory forensics is that the encryption keys are guaranteed to be in RAM. That is, you have the keys in memory necessary to decrypt the data on the disk. This sort of follows by common sense that if the keys weren't in RAM, the machine would not be able to decrypt the data and the system would not work at all. So they're in there somewhere. All we have to do is find them. Now, that's easier said than done, however, because encryption keys are generally small and random. If you think about, AES 256, a commonly used encryption algorithm, an AES 256-bit key is 256 bits long, or 32 bytes. Here is example AES encryption key that I pulled off one of my systems. As you can see, there is absolutely no pattern to it. There's no rule that you can write. There's no header or footer. It's just a bunch of random ones and zeros. Now, there has been suggestion to search for encryption keys to simply take every possible offset in the memory image, consider that as the possible start of an encryption key, and then try using that. And this is actually not a bad idea at all. If you think about a 4 gig memory image, it would have 4 billion possible values. You can try several million keys a second, leading you, a few thousand seconds, but enough time for you to go out and grab a cup of coffee. When you come back, you brute force tested every possible key from a memory image into an encryption algorithm. And that actually works. And there was some folks wrote a paper on that. I believe it was Chivers, and I'm blanking on the other name right now, but they wrote a paper talking about how this is a valuable idea to brute force search a memory image for encryption keys. Works great. The only problem is you have to know what lock the encryption key goes to. In other words, if you're testing to find an encryption key, you already have to know what cipher you're what cipher you're trying to unlock, what the key is going to decrypt. If you already have the TrueCrypt volume in hand, if you already have the protected resource, this strategy works. But if you don't even know if there is TrueCrypt, or you don't even know that one of these products is being used, you can't use the brute force method right away. You have to know whether or not the bits that you're pulling out of the memory image actually decrypt something. You have to know what that something is. In order to explain the method that we can use, though, I need to talk a little bit about how encryption keys are used. In most modern crypto systems, there is an access device which is used to generate or unlock the actual encryption key. Now, that access device can be a biometric thing like your fingerprint. It could be a password or some other authentication token that you have. Either way, those devices are used to generate an encryption key. In other words, your password may be salted and hashed, and then it's that hash which is actually the key used in the encryption algorithm. It's not actually the key which is used to do the encryption and decryption work. Those keys are expanded out into what's called an encryption key schedule, and it's the schedule which is actually used to do the encryption and decryption work. An encryption key schedule consists of a number of round keys, and you may have heard of some algorithms as being 32 rounds or 54 rounds, however many rounds are in the encryption algorithm. And you may have also heard this mentioned when talking about potential breaks in algorithms, that you may hear about an attack against a reduced version of the algorithm, or a version of the algorithm that had a reduced number of rounds. What that means is that the researchers attacked a version of the algorithm that just didn't have as many rounds, has many operations. Each round for the encryption process is to take the plain text, or the output of the step before, and do a basic mathematical operation, shift or rotate, multiplication, something like that. In order to get those round keys, we do what's called key scheduling, which is we take the master key and then run it through a key scheduling algorithm. And that key scheduling algorithm produces the individual round keys which are used during the encryption. Now, the key schedule generally, to generate these schedules, most algorithms use a simple method where the key for round n is simply a function of the round key n-1. So in other words, the first round key is simply a function of the master key. You take the master key and do some manipulation to it. And then the round 2 key is some function of the round 1 key, and so on and so on. So round 3 is a function of round 2, and so on and so on. The neat thing about this, what we're going to use to our advantage, is that for any possible key schedule, we should be able to divide it up into the individual round keys. We'll take a look at what's in the data for round key number 2. Round key number 2 should be a function of the bits that are in round key number 1. We can test that. In other words, we can take the bits that are supposed to be round key number 1, run that function on them, and we should get the bits that are there for round key 2. If we don't get those bits, then what we are looking at cannot possibly be a valid encryption key schedule, and we can move on. If we do get a hit, in other words, if we take what's there in potential round 1, run the function on it, and end up with what's supposed to be there in round key number 2, then what we're looking at cannot be eliminated as a potential encryption key schedule. We can continue running through this random block of data in a memory image, running through all of the round keys. And if we reach the end of the schedule without hitting an error, then the block of data that we're looking at cannot be eliminated from being a potential encryption key schedule. If you listen to the folks who talk about DNA evidence, they use the same kind of language, that the DNA, the person cannot be excluded based on their DNA, meaning they're not saying it matched, but they're saying it cannot be excluded. Same thing with encryption keys, that we are looking for potential encryption key schedules which cannot be eliminated as being invalid key schedules. Once we have found one of those, though, once we've found a potential encryption key schedule, first of all, the odds of finding one of those things randomly is very, very small. Now, we don't know what lock that encryption key goes to, but if we go through a memory image and we end up with 10 encryption keys, remember we can test them, test whether or not an encryption key is valid millions of times a second. Testing 10 of them takes no time at all. So now here's an example of what I was just talking about. You may notice that at the top here we have an AES encryption key, which is just a bunch of not exactly random bits, but good enough for our samples. And then below we would have the key schedule, which is generated by that encryption key. So the first 16 bytes, that first line of the schedule, that would be round key number 1, and then the second line, round key number 2, round key number 3. And there's a defined function to take the bytes of an AES encryption key and turn it from round key to round key. You may notice something interesting here, that the first round key in the AES key schedule actually is the same bytes as the key itself. And this is very, very handy because we can actually get back the original encryption key itself from AES encryption key schedules. It's not always possible in other algorithms, but it is very possible in AES. Now, someone has asked whether or not that's a problem. If we don't get back the original key, if we just have the encryption key schedule from an algorithm, say like the encryption algorithm Blowfish, you only get back the schedule. You don't get back the original key. Well, although it's not very clean, it still can work because we have the encryption key schedule. We have the actual mathy stuff used to decrypt the data. Whether or not we have the original key or not is irrelevant. We can decrypt the data the same way the computer did using that encryption key schedule. I want to go through a real-world example of this using TrueCrypt. TrueCrypt is this absolutely wonderful full disk encryption program. It is free. It has all sorts of great features, and it works on both Windows and OS X and I believe Linux, but I'm not sure about that. But it is it's a great program, and I'm going to show you how through memory forensics you can find the encryption keys used by TrueCrypt and decrypt TrueCrypt protected volumes. Here's how it works. When you enter your passphrase into TrueCrypt, here is my super secure passphrase. It is password 2, not password 1. TrueCrypt computes a header key, and that header key is used to decrypt the header. And the header key is computed by taking a salt, prepending that to the password, and then processing that using an HMAC algorithm. That header key is used to decrypt the header of a TrueCrypt volume. This is a rough schematic of the header of a TrueCrypt volume. As you can see there first, there's the salt value. The salt is stored in the clear. And remember, the salt is stored in the clear because we need it in order to compute the header key itself. And then the header key, which is, the header, which is shown there, and I guess it's kind of pink. That's encrypted with the header key. The only indication that the header has been successfully decrypted is that the header starts with the letters TRUE. When you attempt to mount a TrueCrypt volume, TrueCrypt will take the passphrase that you type in and run the HMAC on it, and if it gets true there in the what should be the header, it assumes that you've entered the right key and continues. If you don't get true, it assumes you haven't entered the right key. Now the header actually contains the master key for the volume, and that master key for the volume never changes. It is stored encrypted in the header. Now the advantage of this system is that when the user changes their passphrase, TrueCrypt only has to re-encrypt the header. The master key for the volume never changes. Now that's a good thing for TrueCrypt. It allows the program to be lazy. It doesn't have to decrypt and re-encrypt all the data every time you change your passphrase. And it's also good for us because even if the system being examined had the passphrase changed, we get the passphrase once, we get the key once, and then we can always decrypt the data. Very, very handy. When you go to create a TrueCrypt volume, TrueCrypt actually displays a whole bunch of information for you. It displays, first of all, the random pool of bits that I was using, and then it displays the header key and the master key. And this is a screenshot from Windows 7 showing TrueCrypt being a TrueCrypt volume being created. And zooming in a little bit on that window, you can see there is actually the red line goes right through the header key, but there are the bytes of the master key. That is the encryption key that is protecting the volume. And that's what we want to get during forensic analysis. During memory forensics, we can take a memory image, run it through this great program called bulk extractor, and have it just do the analysis we described earlier for searching for AES keys. That is, it starts at every offset in the memory image, treats that as a potential AES key schedule, and searches and runs the round key algorithm on it. If it doesn't end up with it eliminates anything that cannot possibly be an encryption key schedule, and at the end of its output, gives you a series of potential encryption key schedules. And so here is one of the files that came out of bulk extractor, and you can see I've highlighted one line here, and this is a potential AES 256-bit encryption key. There is the key right there, and if we go back and look and compare it to the dialog box that we got when creating the TrueCrypt volume, both of these keys started F461CC7B70. Yep, victory. And that through memory forensics, we are able to find the encryption key used to protect a TrueCrypt volume, and now we'd be able to decrypt that TrueCrypt volume. That is winning. Now, Don't get too excited. You can't use that key directly to decrypt the volume. You can't put an encryption key into TrueCrypt and have it decrypt the volume for you. You need special software to do that for you. There are a few commercial programs that will take the keys. Yeah, I have to remain vendor neutral tonight, and so can't talk about what those products are. But they are out there, and you can get it done. Next up in memory forensics, we're going to talk about detecting suspicious behavior. We're going to talk about not just accepting the lies, what the operating system tells you, but actually finding out the ground truth of what's on that system. When you look in Task Manager, you might see an entry for Notepad. Is Notepad suspicious? And I'm asking you, go ahead, is Notepad suspicious? Yes, thank you, Ryan. It does depend. It absolutely depends. On what? Yeah, it actually depends what the actual file. And it depends, which program it is. Just because it's called Notepad doesn't actually mean it's the known good Notepad that Microsoft provides. So using memory forensics, we can start to dig a little bit deeper into what exactly is going on. We can start looking at some Windows structures. First, we can start looking at the eProcess or executive process structure. The eProcess structure holds a 16-character representation of the program name. The program that was called to start this off, to start off each process. And so if we take a look at some hypothetical system that's running, that has Notepad running in the Task Manager, if we look at the image file name, we will probably see notepad.exe in the eProcess. Okay, that sounds good. It's actually the eProcess structure where Task Manager gets a lot of its information. But if we dig deeper, though, we start in structures in the eProcess and keep going down, we can find a version of the command line inside the process parameters. And on our hypothetical system here, we see that the program was called with the command line notepad.exe -m ddosandrews.af.mil. Now, Notepad does actually have a few command line flags that you can give it. I don't think one of them is DDoS, and I know that there shouldn't be anything involving the host name. Notepad does not talk on the network, and if you see Notepad or something claiming to be Notepad talking on the network, you have discovered, in technical terms, bad juju. So, all right, that's not looking so good for our system here that's running Notepad. As we continue looking through the structures, we can see there's another structure in the process parameters called the image file path. And the image file path shows us exactly where the file was on the disk that started off Notepad. And here we can see our version of Notepad started out of c:/evilbin notepad.exe. Although it is possible to customize your Windows installation, generally Notepad does not start out of c:/evilbin. Notepad starts out of Windows System 32. That's where it should live. And if you see it running out of anywhere else, it's probably not so good. Now you will notice, though, that all of these things we've had to examine manually. We've had to take a look by hand. And certainly memory forensics is great for that. You get to see this kind of information, and you would not be able to see these kinds of things just looking at Task Manager or or using Process Explorer, any of those programs. You don't get that kind of information. You have to get a memory image, and you have to take a look at it. What we can do, though, is we can do some small levels of automated analysis. And there will be some false positives here, but small amounts of false positives for an automated method absolutely trump anything that has to be done manually. Oh yes, excuse me. You can see some of this information in Process Explorer, excuse me, but you have to really drill down into it. Thank you, DM McCartney. So we can do automated analysis to find suspicious command lines. Now, most legitimate programs that you run on Windows have an installer program. And when you run that installer program, the installer looks around at your environment variables and looks at shortcuts for basic system directories. And those basic system directories are for things like the program files directory, where applications are supposed to be installed, and for the system root directory, where the Windows files are. And there's one for Windir, where the Windows files live. And generally, your installation program is going to use those shortcuts as the basis of, use those environment variables as the shortcuts it uses when it installs the programs. In other words, when Microsoft Word installs things in the Start menu, those things in the Start menu are actually shortcuts into C:program files, WinWord, whatever, rather than hard coding the paths in case those environment variables change. It's handy. As a result, though, the shortcuts that get put into the Start menu are the same shortcuts that were, or same values that were Microsoft put into the system when you installed it. Now, Microsoft, for whatever reason, always uses a capital drive letter when it sets up these values. And so the shortcuts inside the Start menu and the desktop icons will always have a capital drive letter. Now, because most legitimate programs have an installer, you should see for most legitimate programs in their command line, you should see a capital drive letter. If you don't see a capital drive letter, it means that the program was started without running the installer-generated shortcut. In other words, the program was probably started from the command line. Is having a program started from the command line inherently suspicious? It depends. Absolutely depends. You may have a power user who enjoys starting programs from the command line. I start programs from the command line all the time. Most users, however, don't start programs from the command line. That is an unusual event. And so if you're looking through a system, you can just look for all the programs whose command lines start with something other than a capital drive letter. That gives you all the programs that were started from the command line. Could be power user, could be malware. I don't know. But in general, you're not going to see it for many processes on the system. You will see it. There are actually a couple of legitimate Windows processes, WinLogin specifically, that do start it with a non-capital drive letter, but you can write exceptions for those, and you know about them. There are some rules there. But in general now, we can start automatically flagging things that are suspicious. Here we know nothing about any malware. We know nothing about what we're looking for. We're looking for programs, though, that were not started by a legitimate shortcut. Show me everything that did not have a capital drive letter in its command line. Boom. Here are the 3 processes out of 50 running on a system which might meet your search criteria. Memory forensics can save you time in your investigation. You may not know what you're looking for, but just because it's not doing things the way everybody else does, they stick out more. At this point in the talk, it's time for us to talk about our process ID relationship. Yes, we've been seeing each other for a while now. This talk is going well, but I just want to make sure that we can define the relationship. And in particular, memory forensics helps us define the relationship between processes. The eProcess block skipped ahead a couple of slides there. The eProcess block for every process records not only the process ID of that process, but also the process ID of its parent process, the process that spawned it. We can use that information to build up a tree of who spawned what, a process tree. And in those process trees, I like to divide them into what I call system and user processes. And these are not exact definitions. These are not ring 3 versus ring 0 or user space versus kernel space definitions. These are in terms of the user processes, as I call them, are processes that are manually run by the users. In other words, the user sitting there in Explorer, which is the process running when you're looking at the desktop, you double-click on something in Explorer and it starts up a new process. And so generally all those processes at their root ancestor have explorer.exe. The other processes in the system, I call them system processes, they generally have the system, the kernel, as their primary ancestor. They're part of the operating system. That's things like LSAS and CRSS and those basic low-level system processes. The tree is important because user processes should not be started under system tasks and vice versa. Let's talk about that. So here's the standard tree that you'd see on a Windows XP system. System spawns SMSS, which spawns CRSS, and WinLogon, and these relationships do not vary. In other words, in a legitimate system, you're not going to have a system where spoolserve.exe is launching SMSS.exe. Those don't change. And so on any system, we can take a look at these processes, and we look and find the system process. We find a user process, a command prompt, for example, being spawned by a system process. Again, you've got yourself some bad juju here. And this was taken from a live system. I always thought it was funny because the process in question, the command prompt, was PID 316, and we kept talking PID 316, PID 316, and it sounded familiar to me, and I couldn't think of why. And then I suddenly realized, yes, PID 316, and he who believes in me shall have eternal CPU time. Conversely, in the list of user processes, the processes that are spawned by Explorer, we should never see a system process. So in other words, here's a partial tree of a computer that's running Windows Explorer, and then a couple of browsers, the command prompt. We should never see a system process like LSAS appear in this list. I don't know why this would occur. It seems unusual to me that something like this could exist, but at the same time, it's something to be aware of. And these are, again, rules that we can automate, rules that we can establish and look for. And if you see something that violates these relationships, then you automatically know that something is amiss with the system. You don't have to know exactly what the malware is. You don't have to know exactly that it's which part it's exploring or what it's named. If you simply see a command prompt coming out of any system process, you know something has compromised the computer. Now, what we've been touching on so far is kind of is automated analysis, but now we can do what's called high-low analysis. And you may have heard this used in other contexts. A high-low analysis is a type of analysis where we can automatically identify suspicious behavior without necessarily knowing anything about what we're looking for. What we're doing here is we're using a high-level search. In other words, like getting the same information that would be returned by API calls or by Task Manager, and comparing that to a low-level search, like a brute force search. And by comparing those two sets of information, highlight the differences between them. On a system where everything is working well, the results should be identical. The brute force search for processes should turn up the exact same results that a walk of the operating system's list of processes should turn up. But if there's malware on the system, if somebody's trying to hide something, then you're going to see that there are processes missing from the high-level calls. And those are the ones that we are most interested in. Those are the ones that something is trying to hide. And this is the rootkit paradox in action, that because a malware author attempted to hide something, it makes it stick out all the more. We may have no indicators of compromise on the system that we know of. We may not know what this process is called or its hash or anything about what it looks like, but just because it was trying to hide itself, that means it's precisely what we're looking for. Now, Windows uses a lot of linked lists, and in particular, Windows favors the structures called a doubly linked list. Excuse me, a circular doubly linked list. Now, there is a list head, a magic value that points into the list, and then there's, for each value in the list, these forward and backward pointers which go between the structures. And to walk the list, you start at the list head. You can follow either the forwards or backwards pointers, your choice, until you get back. You walk along examining each structure until you get back to the list head, and then you know you're done. In particular, Windows uses these for holding process information, and there are those eProcess structures that we talked about before, and they exist in this linked list. One of the ways that malware authors can hide or attempt to hide a process is by manually unlinking the process. And you may have heard of this term, an unlinked process. What that means is the eProcess blocks have been manually unlinked. In other words, if we're starting at that process all the way on the left-hand side of the screen, we take its forward pointer and make it point to what the hidden process points to. And same thing for the process there, basically in the middle, we take its backward pointer and make it point to what the hidden process points to. And now what happens is, as the operating system attempts to walk the list of active processes, it gets to one process before the hidden process, follows the pointer, and it ends up walking over the hidden process. It doesn't see it. It doesn't process it. And so if you look at Task Manager, you will not see the unlinked process. It simply doesn't show up during the walk. But if we do a brute force search of the memory image, we will find that unlinked process. And now by just comparing the two lists, we end up with the unlinked process being highlighted. Now, we may end up with leftovers from previous boot. In other words, we'll find a process doing the brute force search which doesn't show up during the walk of the operating system processes, and that's because it wasn't part of this run of the operating system. Now, you may be saying to yourself, I thought that when a computer booted up, it wiped the RAM. Well, it used to. Back when I was your age, when computers were turned on, they went through a post RAM test, and they would overwrite and make sure that they could read every address in RAM. Well, when the wars to make computers boot up faster went down, computer manufacturers took out that post test, and now when you warm boot a computer, anything that was left in RAM could still stick around for the next boot of the operating system. And you will see this. You will see leftovers from a previous boot. It happens all the time. How do you know whether or not what you're looking at is a leftover from a previous boot or not? Well, you can look at the time the system booted, and if that process started before the system booted, then you are looking at a leftover from a previous boot. So to do the high-low analysis, we will do a brute force search of a memory image, looking for process information or whatever structure we want, and then do a high-level walk and then compare the results. And the difference is, whatever they are suspicious unless they're left over from previous boot, which requires a little manual examination, but hopefully you can automate that using your toolkit. And there's how to get the timestamps of the system boot. Okay. Last but not least, I want to talk about the memory images that you already have on the systems that you're examining, and that these are these wonderful opportunities to look back at the machine at an earlier state in time. And both of these are already built into the operating system for you. It's like they were just thinking of forensic examiners. Okay, actually they weren't, but they still help us a lot. Go with it. So Hibernation is a power-saving mode. And what Hibernation does is it takes the state of the system and saves it to the disk. And this was originally intended for laptop users and traveling folks, so that when they were getting on the plane, you could just close the lid of your laptop so the computer would save the state, and then when you got to your destination, you could open your laptop back up again and start working right where you left off. You didn't have to shut down the machine and restart all your programs and open up your files. What Hibernation does is Hibernation saves a compressed memory image and the state of the processor to a file on the disk. What that means is that every time somebody hibernates a computer, it saves a memory image for us to the disk. Now, unfortunately, the memory image, it overwrites, when the system hibernates, it overwrites any previous hibernation file that was on the disk. So it's only a one-shot deal. But one shot is better than no shot. And now that look back in time, that memory image comes from the last time the machine was hibernated. That could be 30 seconds before you acquired the machine. It could be 3 months before you acquired the machine, and the machine could have had a very different configuration then. Maybe the user didn't think that they were going to have their machine seized. Maybe they didn't think that they was going to get examined. Maybe they had confidential documents open. You can get from Hibernation files full content network packets. You can see exactly what the machine was doing on the network 3 months ago. Who knows? It could all be in that Hibernation file. Now, as soon as you enable Hibernation, Windows creates a file on the disk, the Hibernation file, and reserves it. It actually keeps an open file handle to it. It doesn't write anything to that. And it reserves this file, which is it reserves a space on the disk equal to the size of physical memory. So you may find a Hibernation file on the disk which simply contains free and slack space that was on the disk previously. In other words, if the machine was never hibernated, you will not find any Hibernation data in the file, even though the file exists. When the file is written, Windows writes out this compressed memory image. Now, the nice thing is that compressed memory image usually does not take up the equal to the size of physical memory. There is some compression always, and so you're going to find a little bit of slack space at the end of the file, this original disk content, which was free space from from the original contents of the disk. John asks the question whether or not hibernation works the same on Linux. I don't know if it works the same. Sorry, I'm not a Linux expert. Now, the other question I get asked is that when Windows overwrites this hibernation file, is it possible that the next write does not write over the whole file? We might get hibernation file slack. In other words, might get more than one look back. Yes, it's possible, but it's not very valuable. Windows 10 has an algorithm to write out the most valuable pieces of information first, and those get written to the front of the hibernation file. And so what's generally at the end of the hibernation file is not generally valuable. The hibernation file is laid out like this. It has a file header at the start of the file, which tells you the information about the size of memory, what operating system this was, has a timestamp, which tells you when the system was hibernated. There's a processor context record, meaning the exact state of the CPU when the system was hibernated. And then there's a series of page tables and actually the compressed memory pages. And the page tables tell Windows where all of the rest of the contents, where they get written to and ran. Now that header, it has a signature, lowercase hyper or uppercase hyper, and then a whole bunch of other fields. But the most valuable field for us is a timestamp, which tells you, the Windows time when the system was hibernated. Now you may find hibernation file headers slightly different than this. Instead of HIBR, you may find a file that has wake there. When Windows attempts to restore a hibernation file, the first thing it does is it erases that HIBR and writes wake, W-A-K-E. This is to let Windows know that it has attempted to restore this hibernation file. If that restoration fails and the system boots again, attempting to restore the hibernation file again, you'll see this screen, that the last attempt to restart the system, the previous location failed, and asks you, do you want to try that again, or just throw away the hibernation file and continue with the system restart. Jerry asked, is the time in UTC or local time? As with most Windows timestamps, it's in UTC. The last hibernation file that you'll see, or the last hibernation file header that you'll see, is all zeros. This happens after the hibernation file has been successfully restored. Windows wipes the header and just puts in zeros. Now, don't panic. Windows doesn't wipe the whole file. It just wipes the header. So all we lost is the timestamp in the file from the memory image. We still get the entire memory image, and in fact, we still get the processor context record. So you could, in fact, restore the exact state of the system. You have to do a little work to do it, and you can find out the system's current time by examining the memory image itself. The data is all in there. The only thing it actually gives us a piece of evidence that the system state that we saw in the memory image had been restored. That's what it tells us. There is one other option. There can be an arc path in the hibernation file header, and you'll see link at the front. I've never actually seen this on a live system, but it is, according to the documentation, theoretically possible. The hibernation file data itself looks like this. It has this Express header in there, which indicates the type of compression. Windows 2000 used a different form of compression, used LZNT1. Since XP, they've been using this algorithm, which we call Express. And that data can be decompressed by a number of different forensics tools and analyzed. And so then you just end up with a memory image of this snapshot back in time. Along with hibernation files, get a question from Tim. Can you recommend any tools to decompress and read the hibernation file? Honestly, there are a whole bunch of tools that do it. I have my favorites, but your mileage may vary. This is one of those, decompressing hibernation files is actually pretty easy to do, and whatever works into your workflow, whether you're an X-Ways guy or whatever tools your shop uses, test out whether or not those tools already have that functionality. A lot of them do. Along with hibernation files, there are also crash dumps. And certainly Windows these days crashes a lot less than it did in the past, but it still does. And especially if you're looking at the computer of someone who's trying to write malware, the computer may have crashed now and again. It's an unfortunate side effect of writing malicious kernel drivers that you may crash the operating system. When Windows crashes, it has the opportunity to write out a crash dump. These crash dumps were intended for debugging so that you can figure out what the heck just went wrong and hopefully debug it. The crash dump file is you can control exactly where it gets written. And there's this dialog box which controls, first of all, the kind of kernel dump, crash dump file that's written. Windows defaults to a kernel memory dump, or just the kernel portion of memory. But you can also have it write out none, no information from memory, or a full memory dump, which writes out the complete contents of memory. If you could please find all the malware authors you know and have them change the setting to be a full memory dump, I would really appreciate it. Thank you very much. The next thing you can also configure in this dialog box is where to write the crash dump. And you can see here it's set to systemrootmemory.dmp. It's not actually trivia, but when Windows crashes, the operating system has now crashed. It does not. The operating system doesn't. It would not be a good idea to attempt to open up a new file handle at this point. You're already in an unstable state. Just get out of here as fast as possible. As a result, what Windows does is actually writes the crash dump data to the paging file, and it's on the next reboot that the paging file is copied over to the file specified in this dialog box, and the memory dump file is created. The crash dump file format, it reminds me of an NTFS file in that there's a file header in this series of runs, and the header has a listing of for each run how big it is and where it starts, and you can put together then portions of memory. You usually don't get full memory image. Like I said, the default is a kernel memory image, but you get some of it. And again, there are a number of tools that you can use to not only analyze crash dumps, but there are some tools to create crash dumps. My favorite is this one by Mark Rusinovich called Not My Fault, which allows you to pick different kinds of ways to crash the system and create a bug and then crash it. And if you're going to attempt crash dump analysis, I highly recommend using Not My Fault to make some crash dumps. See what it looks like. Find the data that's in the paging file before it gets copied over. Take a look at what the system does when it's crashing, and then use that in your investigations. So in this talk, we've covered encryption keys. We've talked about how you can look for encryption key schedules using those automated methods, the round keys, and using the round key algorithm to determine them one from another. We looked at command lines. We looked at a simple process called Notepad could have command line switches, which help us determine whether or not that process is evil or not. Then we looked at process ID relationships, talking about system processes versus user processes, and how a user process should never spawn a system process, and vice versa. We did high-low analysis, where we looked at how looking at information in brute force search for eProcess blocks versus a walk of the operating system structures was able to help us to identify automatically any hidden processes. And the more that they attempt to hide themselves, the more we will be able to see them. And then finally we talked about hibernation files and crash dump files, these wonderful looks back into a system's history. And with that, I'm open to any questions you have.
And our first question is, does this approach cover solid-state disks?
What I think you're asking about is an analysis of SSDs, of hard drives. And no, we're talking about the RAM of a system here. We're not talking about anything that's on the disk.
And our next question is, do you have any resources that you can recommend for further reading?
Oh, absolutely. The absolute Bible of this stuff is a book by Mark Rusinovich. Oh God, I'm going to butcher the other names. David Solomon and Alex Anescu, called Windows Internals. These books, and there's actually several volumes to these books. Now, it's a two-volume set, and there are multiple editions of the books, are absolutely the Bible to how Windows works internally. Anything you could ever possibly want to know. That is absolutely diving in at the deep end, but you can go down to the store right now and buy a copy of the books. Certainly we talk about all these kinds of topics in more detail in the class I teach. It's 4/5/26, and there are going to be iterations of that course in March in Orlando, in May in San Diego, and July in Washington, D.C., and I believe that there are other dates set up for 2013, which, let me just show you, it should be right here. June in DC, and July in Austin, Texas. That's where the course is going to be taught. Hopefully that answer met with your seal of approval.
And our next question is there a tool to wipe Hibernation files and crash dump info from hard drives?
In order to wipe those files, first you'd have to turn off Hibernation, and then you can just erase the file normally. Crash dump files, you should just be able to erase the files. They're not protected in any way. So the del tool from the command prompt would be sufficient to erase either file once Hibernation has been disabled.
And I'd just like to let everybody know we still have a couple minutes, so if you do have any questions, please feel free to type those to moderators through the chat window. And our next question, if you turn off Hibernation, does Windows automatically delete the file?
I don't know. I don't think it does. I think you have to turn it off and then manually delete it.
And our next question is, does SIFT have the tools to perform the analysis you just highlighted?
Absolutely. The SIFT contains a number of tools to include the volatility framework, which is pretty much is becoming the de facto standard for doing memory forensics.
And Chris asks, would it be better to disconnect a LAN cable from a PC and leave it running for better memory analysis?
Chris, you don't really specify what would be better than. I'm assuming pulling the plug. But yes, disconnecting the LAN cable is a good idea when doing incident response.
And Laura asks, is the bulk extract tool that you mentioned in the encryption key section a commercial product or open source?
Great question, Laura. The tool is called Bulk Extractor. It is free and open source, and it also comes in the SIFT as well.
And short of running strings on memory, what can you do with a corrupted memory dump?
It depends. It depends on the nature of the corruption. Some of the memory forensics tools can deal with partially corrupted memory images. Some can't. If you have a specific case in mind, I'd love to talk to you about it offline. My email address is research@jessekornblum.com, and if it's something you're able to share, I would be very interested in looking at a corrupted memory image, and especially knowing how it was corrupted.
And we still have a few minutes. If you have any questions, please feel free to type those to moderators.
While we're waiting for questions, I just want to say thank you very much for everyone for attending today. Very much appreciate your time. Obviously, I'm going to stay here and keep answering questions so long as people ask them, but thank you very much for attending the webinar tonight.
And our next question is, can you expand more on utilizing Bulk Extractor to look to keys? Is there a setting in BE to look for these keys?
Yes, in Bulk Extractor, the versions I've been using, you use the lowercase e and then space AES, or is it just lowercase e? This is one of those things I have to look at the man page. But yeah, it's a simple command line flag to tell it to look for crypto keys. The crypto keys then are saved out to a file on the disk called crypto.txt, and just all the other keys are right there. There was one other question from Edward Park, who asked if there were any open source tools to capture RAM. Yes, Edward, there are several. My preferred one is the Win32DD tools, written by Matthew Swish, and they're available on his website.
And is it possible to inject malware or process in Hibernation files such that it would run on resume?
You know, I have not seen it done, but I would imagine it would be possible, yes.
Thank you so much, Jesse, for your great presentation and for bringing this content to the SANS community. To our audience, we really appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.